Right, so we next continue with this exercise, and here we have to prove corollary 6 for 17, the 17th item in this section. So let's start by recalling the statement of this corollary. This corollary is nothing but that one which has the name 0 test for sequences. Let AN be a sequence of real numbers. Then we are, because our aim is not to write the exact statement but to just recall what it says, I am going to write like this. The exact statement says this: then this limit exists and is 0 if and only if this limit exists and is 0. The sequences differ by having and not having that absolute value. Okay, so that is the first part, and in the second part we are asked to say something about this, the state of the corollary if this 0 is replaced by some other number. We will see that in that case the corollary is not necessarily true. So let's start the solution. We first prove the corollary. Let's first assume that this limit, okay, the one involving that sequence with absolute value, this limit is equal to 0. Note one thing, that if you see a statement like this, an equation like this, it says two things at once. The first is that this limit exists, and the second thing is that it is equal to 0. So existence of the limit is a part of this equation. Since these inequalities are true, for all the indices, these inequalities we already know are true from elementary properties of absolute values of real numbers. It follows from the squeeze test, which is corollary 14. That this limit exists and is equal to 0, because we have these inequalities. So both these sequences, we have two sequences, actually 3, but the outermost sequences are two. One of them is this one, it has its terms absolute value of an, and the other one is the negative of the absolute value of an. Both of these sequences converge to 0. In fact, to conclude that this leftmost sequence converges to 0, you have to really apply that algebra of limits of sequences, where you have this now. If your say some sequence bn has limit b, then if you multiply all the terms by some constant real number c that does not change with n, then this sequence also is convergent and it converges to b. So to say that this sequence converges to 0, we have taken c equal to -1, that's all. But we are not mentioning those things, okay? Those things are understood and they are in the background. And that is why, because both the outermost sequences converge to 0, so by the sandwich theorem, corollary 6,4,14, the limit of this sequence also exists and it is equal to 0. So we have proved one half of this corollary, namely this implication. This implies this. Now the converse. Conversely, assume that the limit of the original sequence exists and is 0. We now want to prove this limit. This time, however, we cannot use sandwich theorem, or I mean the squeeze test, but we will go to the definition of limits. We want to show that this limit is equal to 0. So we start by choosing an epsilon. Choose a positive real number epsilon. Then, because of this limit, there exists an integer n greater than or equal to m such that this difference is less than or equal to epsilon. For all integers n greater than or equal to n. But then we also have this thing -0 equal to this less than or equal to epsilon for all n greater than or equal to n. Note that these two real numbers are actually equal and both of them are equal to the absolute value of an. In general, in this type of situations, there is one general inequality that one can use. It is that if you have any two real numbers a and b, then this inequality exists. This can sometimes be used in this type of situations. In this particular case, of course, we have equality, so our job is done. So now, by the definition of limits itself, the limit of absolute value of a n is 0 as n tends to infinity. So that completes the proof of the corollary. Now we come to this next part. What happens if we replace 0 with something else? The conclusion of the corollary, or rather we can simply say the corollary, is not necessarily true. If 0 is replaced with a non-zero number. To see that, this sequence whose terms are alternately -1 and +1 is divergent. This we already know. It is not a Cauchy sequence, so it cannot be convergent. But the sequence which is obtained by taking the absolute values of the terms of that sequence converges to 1. So that means in this equivalence, that we have in that corollary, replacing 0 with 1, for example, does not work in general. If you take in place of a in this sequence, this statement is false. Now what am I saying? This statement is true, but this one is false. Okay, so they are not equivalent. However, at the same time, it's not that always this type of thing will happen. For example, instead of taking this sequence, had we taken the constant sequence 1 as a n, then this equivalence is true, because in that case on both sides the limits actually are equal to 1. They exist and both of them are equal to 1. So in general one cannot say anything, it depends on the sequence. If we change this number from 0 to something else, so that's why we are saying not necessarily true. And the solution ends here. Next, we have seen what a limit point of a sequence means. In that definition of a limit point, the limit point is whatever it is. The definition of course comes, but before that we declare that a limit point of any sequence of real numbers is itself a real number, it is finite, and then the other conditions come. In this exercise, however, we are going to extend that definition to include plus infinity and minus infinity as limit points by giving some extra conditions. So let's see what the author says. Let us say that a sequence of real numbers has plus infinity as the limit point if and only if the original sequence has no finite upper bound and minus infinity as a limit point if and only if the sequence has no finite lower bound. So here what we are saying, that if the original sequence does not have a real number as an upper bound, then we say that plus infinity is a limit point of the sequence. Just like that, if the original sequence does not have any real number as a lower bound, then we say that minus infinity is its limit point. Okay, so this is something extra to our definition of limit points. Now what with these new definitions? With this definition, show that the limit superior of an is a limit point of an and furthermore that it is larger than all other limit points. Of an. Okay, so tau is extending it even more. In other words, the limit superior is the largest limit point of a sequence. To me, these sentences seem unnecessarily long because we have got the point, but to Terence Tao, I think these sentences are very short. Why? Because he is an extremely fast thinker as well as an extremely fast speaker, and I am just the opposite. I think extremely slowly and I say also things extremely slowly. So maybe that's why I feel these things are very long. In other words, the limit superior is the largest limit point. Of a sequence, and similarly show that the limit inferior is the smallest limit point. It's not over yet. One can use proposition, yes, of course. Proposition 6 for 12 in the course of the proof. Okay, there are a number of things here. This portion we have seen. Now what we are saying with this definition, show that the limit superior, the upper limit of the sequence, is the limit point of the original sequence. Note that this is an extension of one of the parts of proposition 6 for 12, where we say that the upper limit when it is finite is a limit point of the sequence. Here, however, this fact is unconditional. We are not putting any condition on the finiteness or infiniteness of this upper limit. Whatever it is, it's now going to be a limit point, and to account for that infinite case, we have this definition. Something else also I want to say here. You see this IFF, you probably already know it. It is a short way of writing the phrase if and only if. And don't forget that in a definition, if and only if mean the same thing in a definition, not somewhere else. Okay. Whether you write if or you write if and only if, they mean the same thing. Okay, so we have to prove that this is a limit point of the sequence and it is larger than all other limit points. So it is the largest limit point of the sequence, and similarly limit inferior has to be proven to be the smallest limit point of a sequence. Okay, so let us see the solution, what we can do here. In the beginning itself, for our ease of writing, we are going to denote it by something. Let A denote the limit superior of an, and if A is finite, then automatically it's a limit point. Then by proposition 6, 4, 12, but which part? Have I written that here? E. A is a limit point of the sequence an. Okay, now next assume the case where A is plus infinity. Assume A is plus infinity. Then, so what is A? A is an infimum. It's the infimum of all these suprema. This type of notation probably I have written for the first time. It is nothing but this thing. Instead of writing like this, to make it more compact horizontally, I have placed the condition, this condition here below the infimum. It's like writing a sum and then putting some condition here. Say the sum varies over some lambda, say a lambda, where lambda varies over s, that's something like that. Okay. Now it's the infimum of a set, and that infimum is plus infinity, the largest possible extended real number. And because it's the infimum, it is going to be less than or equal to all the elements of this set. However, since it's the largest possible extended real number, so all the an classes within this range must themselves be equal to plus infinity, because otherwise there is no other choice. This implies an plus is plus infinity for all possible capital N. In particular, am plus is plus infinity, that is, okay, now what is am plus? Because here we have taken m, so all the terms of the original sequence are here in this am plus. That is, the am plus by its very definition is the supremum of the sequence itself. And that is plus infinity. So our sequence supremum is plus infinity, means the sequence does not have a finite upper bound. But then by the definition we have seen in this exercise, plus infinity is a limit point, and that plus infinity now is a. This is a limit point of our original sequence. So even when the limit superior is plus infinity, that is a limit point according to our new definition. One more case is there. Next, assume that the limit superior is minus infinity. Then by proposition six, 4, 12, I never seem to be able to remember these parts. I mean, which part is which one? C. The limit inferior of an is minus infinity. What have we done here? In this part of the proposition, we have this inequality. This inequality. Now this is minus infinity because this is our a. So it is the smallest possible extended real number. So this one should also be equal to minus infinity. That is the only possibility. So that's what we have written here. Okay, so that means this is minus infinity. That is, if we now apply the definition of limit inferior, then limit inferior is what? Supremum of a bunch of infima this is equal to minus infinity. Supremum is minus infinity because all these an minuses are less than or equal to this supremum, which is minus infinity. So all the an minuses must themselves be equal to minus infinity. This is equal to minus infinity for all the possible indices. In particular, am minus is also minus infinity. That is, am minus, just like that one, am plus is the infimum of the entire sequence, because our index is now starting from m, so we haven't removed any term, so we have the full sequence. This is equal to minus infinity. Thus, our sequence has, because the infimum is minus infinity, it has no finite lower bound. Or saying more loosely, it is not bounded below. But when a sequence is not bounded below by a real number, then minus infinity is by definition a limit point of the sequence, and that's what the limit superior is now. Okay, so we have shown that whether the limit superior is a real number or plus infinity or minus infinity, it is a limit point, taking everything into consideration, the old definition as well as the new definition. Next, what we are going to show is that it is the largest limit point. So for that, let C be any limit point any limit point of our sequence. Our aim is to show that C is less than or equal to A, the limit superior. We haven't touched the limit inferior yet, but you can guess what I am going to do. At the end of the solution, I will just mention that one can simply handle the limit inferior case, which however you have to handle. Note one thing, about this sentence. This sentence, unlike how we would interpret this sentence previously before this exercise, now the meaning is different, a little different and a little more general. Previously, in our original definition of limit point, the limit point was by definition a real number. Now that is not the case. So this c can very well be minus infinity as well as plus infinity, and in fact we have to consider those cases. So first let us see when c is c is in R, what happens. If c is a real number, then by again proposition 6 for 12, but which part? D. C is less than or equal to the limit superior. In part D, what we had is this: the limit inferior L minus, if you recall the notation that we used, is less than or equal to the limit point C, which is less than or equal to the limit superior, if C is the limit point according to the old definition and hence a real number. And also recall that in these inequalities we were not bothered about whether these are finite or not. Regardless of that, these inequalities are true. C has to be finite. Okay, so that's what we have written. This A now is L plus. So that is one case. And there is one other case which can be handled very easily. If C is minus infinity, then of course C is less than or equal to A, and this inequality, it just simply follows from the fact that C is minus infinity. You don't need anything else. It is the smallest extended real number, so that's why we have this inequality. Now assume the case where C is plus infinity. So the hypothesis that C is a limit point of our sequence means what? And it is plus infinity. It means by definition that the sequence has no finite upper bound. Then the sequence has no finite upper bound, and in this case we claim that all these suprema are going to be plus infinity for all the possible indices. This is our claim now, because if we are able to prove this claim, then the infimum of all these suprema will also be equal to plus infinity. In other words, the limit superior or small a will be plus infinity, making it greater than or equal to C, in fact equal to C. But this is our claim, so we are now going to prove this claim by contradiction. Contrary to this, we suppose that some an not plus is a real number. For some n not greater than or equal to m. See, contrary to this claim, actually we should have written there is some such integer n naught for which a n naught plus is not equal to plus infinity. However, in place of that we have written this. Not being plus infinity does not mean being a real number. That other cases also there, being minus infinity. That, however, will not happen here. We are going to mention that fact, but we won't write the reason. I will show you the reason. Note that an plus is never minus infinity, and the reason is this. Suppose your an naught plus itself is minus infinity. What is an naught plus by definition? By definition, it's the supremum of this set plus 1 and so on for higher values of the indices. This is minus infinity. Because the supremum is greater than or equal to all the elements of this set, so all of these elements must be less than or equal to minus infinity. However, that would force all these elements themselves to be equal to minus infinity. But that is not possible. Why? Because these are all real numbers. We are dealing with a sequence of real numbers. So that's why we don't have this case. It's always like this. So, contrary to this, our supposition actually implies that this is a real number. Okay. Because this argument is very easy to guess, so we have decided not to make it a part of the solution. But then the finite, okay, not like this is not actually the language, but then our sequence has the following finite upper bound. This number but how is it an upper bound of the sequence? That is not again not a part of the solution because one can show that easily. However, for the sake of completeness, let me show you how that is an upper bound for the sequence. Okay. So to be an upper bound for the sequence, this number must be greater than or equal to all the terms of the sequence. But do you see why that this number is finite? What is this number actually? It's a sum of two real numbers. One of them is the maximum of these absolute values. Since here all the ai's are real numbers, so this itself is a real number. In fact, it's a non-negative real number because of the presence of absolute values. And because of this condition, an naught plus being itself real, this is also a non-negative real number. So that means this is a finite number, extended real number. How is this an upper bound for the sequence? Let's call this number temporarily for the sake of this small argument L. Now say we have an where n is in this range. You have to understand one thing, that our n naught itself may be equal to m. In that case, this second real number in this sum is not there. Okay, in that sense it has been considered. But if of course n naught is greater than m, then we would have something, at least one absolute value here. Anyway, so in this range, what happens to an is this. An is of course less than or equal to its own absolute value, and because n lies in this range and this is the maximum of all those numbers, so this is less than or equal to this maximum, and that maximum in turn is less than or equal to this, because this is a non-negative real number. And if our n lies in this range, then what happens? Then an is less than or equal to an naught plus. Why? Because an naught plus by definition is the supremum of this set. So for our particular n, this an is here somewhere, so that should be less than or equal to the supremum of the set, and this itself is less than or equal to its own absolute value, and that is less than or equal to plus that maximum. Note that just like this is a non-negative real number, this maximum itself is also a non-negative real number, because it's the maximum of finitely many such non-negative real numbers. And this is how this L is a finite upper bound of our sequence. Okay, so now that we have understood how it's an upper bound, we can wrap this part off. We are not keeping L also because we don't need this number any more than this. But this is a contradiction. It contradicts the fact that this has no finite upper bound. This is a contradiction, and so our supposition is wrong. Last supposition. The claim is thus established, and because of this claim, let me pour some ink to it. So all our an classes are now class infinity. So the limit superior which is the infimum of this suprema itself is plus infinity. Hence, in this case also C is less than or equal to A, and in fact C is equal to A, and both of them are plus infinity. So that's why the limit superior is the greatest, the largest limit point, and one can similarly handle the limit inferior, and we end the solution here, leaving the limit inferior to u. Using the definition, in the previous exercise 648, construct a sequence an of real numbers, of course, which has exactly 3 limit points. At minus infinity, 0 and plus infinity. So such a sequence now has to be constructed. Two of those limit points are the infinite extended real numbers, and one of them is 0. If you think of it for some time, you will easily get any such sequence. So without too much explanation, we just simply write Do you see the pattern? Let me write a few more. And that's just it. Ideally, we should not keep the solution like this. We should in fact properly define the sequence by saying what its nth term is for any positive integer n, because that's how the indices are varying here. You can clearly figure out what to write. For example, the first term is -1, second, third, the fourth term is -2, fifth, sixth, seventh, the eighth term is what I'm saying, first term is -1, second, third, fourth term is -2, fifth, sixth, seventh term is -3. So like that, those terms are progressing. Then the second one is 1, the fifth one is 2, the eighth one is 3, and like that these reciprocals also can be figured out. So what I am saying here is that in the rigorous definition of this sequence, it will be partly defined for 3 different types of indices. Okay, I leave that to you to actually rigorously write the definition of the sequence. Then from that definition, you have to show that -infinity is a limit point, which one in fact can see quite easily because the sequence does not have any finite lower bound because of the presence of these terms, these negative terms, -1, -2, -3, -4, and it goes like that. Just like that, the sequence also does not have a finite upper bound because of 1, 2, 3, 4, etc. So -infinity and +infinity are both limit points of this sequence, and a part of the sequence is going towards 0. So 0, of course you have to show using the actual definition of limit point that 0 is also a limit point of this sequence. After having these things, then you somehow argue that there is no other limit point. Okay, to see that you just use all the results that you have seen about limit points, and you can directly argue from this sequence itself that -infinity, 0, and +infinity are the only limit points. So this entire thing is left to you. So this is only a hint. Only I have given you the sequence, the rest you have to do. And then we have the 10th one. Let an be a sequence of real numbers and let Bm be also a sequence of real numbers. Be another sequence of real numbers such that each Bm, that means each term, each element of this sequence is a limit point of the first sequence. Let C be a limit point of the second sequence. Then we have to show that C is also a limit point of the first sequence. Prove that C is a limit point of An. In other words, limit points of limit points are themselves limit points. Of the original sequence. So if you collect the limit points of a sequence, in this one there are 3. However, you may have a sequence which has infinitely many limit points, so that you can create a sequence out of those limit points, and then it may happen that in that sequence also you find a limit point C. Then this will be a limit point of the original sequence. In other words, oh no, we cannot say that. Okay, no, I was thinking that this C will be equal to 1 Bm here. No, it is given that each Bm is a limit point of the first sequence, not that this sequence has all the limit points of this sequence. That is not given. Had that been the case, C would have been an element here. But anyway, if you collect limit points and then find a limit point of those limit points, then that itself is also a limit point of the original sequence. So taking limit points of limit points, we don't get any new kind of point. We get limit point, a limit point back of the original sequence. So that's what we have to show. So what is it we have to prove here? We have to prove that C is a limit point of an. So we start by choosing an epsilon and a stage in a stage say k greater than or equal to n. Choose epsilon greater than 0 and an integer k greater than or equal to n. What we have to show in order to conclude that C is the limit point of this, we have to show that there exists an integer n greater than or equal to k for which the distance between an and C is less than or equal to epsilon. This is what we have to show. So we will now search for this n. And the hypothesis given to us is of course these things. The first is that each Bm is a limit point of an. Since each Bm is a limit point of an, there exists an integer nm greater than or equal to k such that ANM minus BM is less than or equal to epsilon by 2. There are some things to be explained here. Bm is a limit point of this sequence. So for this epsilon and this stage, we would get an integer greater than or equal to that stage such that the corresponding A term and the Bm term, the distance between them is less than or equal to, we have chosen in place of epsilon, we have decided to write epsilon by 2, which we can do. But why this suffix m? Keep in mind that this thing that we have said actually depends on m, depends on this Bm, and hence it depends on m. To show that dependency, we have written n suffix m, and we are in fact going to mention this. Note that this is in fact true for all m. So m starts from capital M, so we write this. That means it's not a single inequality. Actually, excuse me, actually these are infinitely many inequalities. You keep on changing m, each m gives you an integer in m. We don't know whether these integers are equal or not equal, greater. We don't know and we don't care. The only thing we know is that each such integer is greater than or equal to k, and for which this inequality is true. Okay, so we have used only this part of the hypothesis that each bm is a limit point of an, but now we also use this one, that c is a limit point of these bm's, since c is a limit point of this bm's, there exists an integer there exists an integer for which something will happen, but that integer we would take as what? We would take that integer to be greater than or equal to the maximum of k and capital M, such that this distance is less than or equal to epsilon by 2. So here we have used the fact that c is a limit point of Pm. So epsilon is there, and what is our, in this case we have taken the stage to be k. In this case, what is the stage? The stage is maximum of k and m. Just like k has to be greater than or equal to n, here the index starts from capital M. Does this stage also satisfy such an inequality? Yes, because it's the maximum. Okay, so because of this we are getting an integer m, not for which this will happen. Then what is the distance between a, n, m naught? Okay, this may be slightly confusing, and c. By the triangle inequality for distances, this is less than or equal to this minus bm naught plus the distance between bm naught and c. This is already this is a fixed real number, right? Here nothing is changing actually. This is less than or equal to epsilon by 2, that we know. But what about this? The question is, can we take m equal to m naught here? We in fact can, because whatever we have written here is true for all m greater than or equal to m, and our m naught, just like the it is greater than or equal to m, is also greater than or equal to k. Why? Because this maximum itself is greater than or equal to k, and that is why Oh no, that's not what I wanted to say. This is of course greater than or equal to k, but this is what I need. Because now you see our m naught is greater than or equal to m, and that is why we can take this m here. There exists an integer this. Where is this m coming from? Bm, where m comes from here. M should be greater than or equal to capital M, and this inequality takes care of the fact that m naught becomes greater than or equal to capital M. So Bm naught is an element in this sequence, and because of that, from that Bm naught we get a corresponding inequality that involves this distance. So this is also less than or equal to epsilon by 2. We have thus found an integer in let me continue from there, no need to clutter the space. An integer in m naught greater than or equal to k, for which this distance is less than or equal to epsilon. Do you see how this is coming? In the process of getting these inequalities, we have this in the middle, and this is true for all m. So in particular, this inequality, just like this one, is also true for m naught. That's what we have written, and this in m naught itself is an integer greater than or equal to k, for which this is true. In other words, if you if this notation seems somewhat confusing, you can write like this. We have found an integer n equal to n m naught. So we are talking about n m naught, but we are calling it n for simplicity. So that's it. We have found one n that exceeds that chosen stage k, such that the distance between a n and c is less than or equal to epsilon. This proves that c is a limit point of our original sequence. This completes the solution, and it also completes this set of exercises. After this, we have another section where we will calculate some standard limits, that is limits of some well-known standard sequences. but that we will do in another video next Sunday. And on coming Tuesday we will have a vector space upload from Herstein's topics in algebra. So I'm ending the video here itself. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address. So see you on Tuesday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.